floating neutral can cause the symptoms you described. Firstly, a lost neutral means that the neutral wire has been broken somewhere in the circuit, preventing current from returning to the electrical panel through its intended path. Secondly, electricity from the hot wire may find an alternate return path through the grounding system. Because the grounding system is usually connected to the neutral at the electrical panel, it can act as a substitute. Thirdly, when you measured 120 volts from ground to hot, you measured the voltage difference between the hot wire and the grounding system. The grounding system was acting as the neutral. Fourthly, you should have measured close to 0 volts from ground to the open neutral wire if your meter was functioning properly. There was no complete circuit for current to flow through to return back to the panel. Fifthly, when a circuit is working correctly, you should read 120 volts between the neutral and hot wires. The presence of voltage between neutral and hot signals that the neutral wire is not properly connected, creating an imbalance. To solve this issue, find and repair the broken neutral wire. Check all connections, junction boxes, and fixtures along the circuit. Reconnect the neutral wire and the circuit should function correctly with expected voltage measurements between ground, neutral, and hot. It is not safe to connect the ground and neutral wires. Ground and neutral wires have different jobs, and they should not be combined. The neutral wire carries current back to the source, typically the electrical panel, completing the circuit. It provides a low impedance path for the return of current under normal operating conditions. The grounding wire provides a path for fault current to flow back to the source, tripping a circuit breaker or fuse and disconnecting the circuit in the event of a fault, such as a short circuit or insulation failure. It is designed to protect against electrical shock and prevent equipment damage. The ground and neutral wires are connected at one point at the service entrance of the electrical system. This ensures a common reference point for voltage. Downstream from this point, the ground and neutral wires are kept separate. Connecting the ground and neutral wires together downstream from the service entrance can create multiple paths for current to flow, which can lead to several problems. One problem is ground loops, which can cause noise and interference in electronic equipment. Another problem is stray voltage, which can create a shock hazard. Lastly, connecting ground and neutral can compromise the effectiveness of the grounding system and increase the risk of electrical shock. To prevent electrical hazards and ensure proper circuit operation, keep the ground and neutral wires separate throughout the electrical system, except at the designated bonding point at the service entrance. Locate and repair the open neutral wire instead of trying any shortcuts. Here are some additional considerations when troubleshooting a floating neutral. Firstly, use a properly calibrated voltmeter to take voltage measurements at various points in the circuit. This will help pinpoint the location of the open neutral. Secondly, visually inspect all wiring connections, terminals, and splices for signs of damage, corrosion, or looseness. Pay close attention to connections in junction boxes, outlets, and light fixtures. Thirdly, use a non-contact voltage tester to check for the presence of voltage along the neutral wire. This can help identify the section of the wire where the break is located. Fourthly, if you suspect a faulty connection within a device such as a switch or receptacle, disconnect the device and test the continuity of the neutral wire using a multimeter. Fifthly, if you are unable to locate the open neutral using the above methods, consider hiring a qualified electrician to perform a thorough inspection of the circuit. Remember to always disconnect power to the circuit before performing any electrical work to prevent electrical shock or injury. Furthermore, it's crucial to differentiate between a true floating neutral and other wiring issues that may cause similar symptoms. For example, a high resistance connection on the neutral wire can also lead to voltage imbalances and erratic circuit behavior. In such cases, the voltage drop across the high resistance connection may cause the neutral voltage to rise above 0 volts, resulting in voltage readings similar to those seen with a floating neutral. In addition to the voltage measurements, also inspect the condition of the wiring insulation. Damaged or deteriorated insulation can lead to leakage current, which can affect voltage readings and circuit performance. Also, check for any signs of water damage or moisture in the electrical system, as moisture can create conductive paths and affect the integrity of the neutral connection. When working on electrical circuits, Always follow safe work practices and wear appropriate personal protective equipment, such as insulated gloves and safety glasses. Lastly, be aware of the specific requirements and regulations outlined in the National Electrical Code, also known as NEC, and any applicable local codes or standards. The NEC provides detailed guidelines for electrical wiring, grounding, and safety, and it's important to adhere to these guidelines to ensure safe and reliable operation of electrical systems. When you encounter a situation where you suspect a floating neutral, it is important to follow a systematic troubleshooting approach to accurately diagnose and resolve the issue. Firstly, gather information about the circuit. Understand the circuit layout, including the location of outlets, light fixtures, and appliances connected to the circuit. Review any available electrical drawings or diagrams to gain a better understanding of the circuit configuration. Secondly, identify the symptoms. Document the specific symptoms you are observing, such as lights not working, outlets not providing power, or unusual voltage readings. Note any recent events or changes that may have preceded the problem, such as electrical storms, power surges, or recent modifications to the electrical system. Thirdly, perform a visual inspection. Carefully inspect the circuit for any obvious signs of damage, such as loose wires, corroded connections, or damaged insulation. Pay close attention to junction boxes, outlets, switches, and light fixtures. Fourthly, take voltage measurements. Use a properly calibrated voltmeter to take voltage measurements at various points in the circuit. Measure the voltage between the hot wire and the neutral wire, the hot wire and the ground wire, and the neutral wire and the ground wire. Compare your measurements to the expected values. Fifthly, perform continuity testing. Use a multimeter to perform continuity testing on the neutral wire. Disconnect the power to the circuit and verify that there is continuity between the neutral wire at the electrical panel and the neutral wire at various points along the circuit. A lack of continuity indicates an open neutral condition. Sixthly, isolate the problem. If you have identified an open neutral condition, try to isolate the location of the break. Disconnect sections of the circuit and perform continuity testing on each section to narrow down the location of the problem. Seventhly, repair the issue. Once you have located the open neutral, repair the break by reconnecting the neutral wire using appropriate wiring techniques and connectors. Ensure that all connections are tight and secure. Eighthly, verify the repair. After completing the repair, verify that the circuit is functioning properly by taking voltage measurements and testing the operation of outlets, lights, and appliances connected to the circuit. Ninthly, document your findings. Keep a detailed record of your troubleshooting steps, voltage measurements, and repairs. This documentation can be helpful for future reference and troubleshooting. In addition to the above steps, consider the following tips for troubleshooting floating neutral conditions. Firstly, use a circuit tracer. A circuit tracer can be used to trace the path of the neutral wire and identify any breaks or discontinuities. Secondly, check for loose connections. Loose connections are a common cause of floating neutral conditions. Check all wire connections, terminals, and splices for tightness and corrosion. Thirdly, test the grounding system. Verify that the grounding system is properly connected and functioning correctly. A faulty grounding system can exacerbate the effects of a floating neutral. Fourthly, consult with a qualified electrician. If you are not comfortable working with electricity or if you are unable to resolve the issue on your own, consult with a qualified electrician. Electrical work can be dangerous, and it's important to take proper safety precautions. Let's delve deeper into how voltage measurements can help you diagnose a floating neutral. Firstly, normal conditions. In a properly working 120 volt circuit, you should measure approximately 120 volts between the hot wire and the neutral wire. You should measure approximately 120 volts between the hot wire and the ground wire. You should measure close to 0 volts between the neutral wire and the ground wire. Secondly, floating neutral. With a floating neutral, you may measure unusual voltage readings. You may measure a lower than expected voltage between the hot wire and the neutral wire. You may measure a higher than expected voltage between the hot wire and the ground wire. You may measure a significant voltage, possibly close to 120 volts, between the neutral wire and the ground wire. These voltage readings indicate that the neutral wire is not properly connected and that current is flowing through the grounding system. It's important to note that the voltage readings can vary depending on the load on the circuit and the location of the open neutral. To accurately diagnose a floating neutral, it's best to take voltage measurements under different load conditions. For example, you can take measurements with all appliances and lights turned off, and then take measurements with some or all of the appliances and lights turned on. Compare the voltage readings under different load conditions to identify any significant changes. Let's explore the dangers of connecting the ground and neutral wires. Firstly, electrical shock. Connecting the ground and neutral wires together creates a parallel path for current to flow. In the event of a ground fault, current can flow through the grounding system and back to the electrical panel through the neutral wire. This can energize metallic parts of appliances and equipment, creating a risk of electrical shock. Secondly, fire hazard. Connecting the ground and neutral wires together can overload the neutral wire, causing it to overheat. This can damage the insulation of the wire and create a fire hazard. Thirdly, equipment damage. Connecting the ground and neutral wires together can interfere with the proper operation of ground fault circuit interrupters, known as GFCIs. GFCIs are designed to detect ground faults and quickly disconnect the power to prevent electrical shock. When the ground and neutral wires are connected, the GFCI may not be able to detect ground faults, which can lead to equipment damage and increased risk of electrical shock. Fourthly, code violations. Connecting the ground and neutral wires together is a violation of most electrical codes, including the National Electrical Code, also known as NEC. Electrical codes are designed to ensure the safety of electrical installations, and it's important to follow these codes to prevent electrical hazards. To prevent these hazards, it is essential to keep the ground and neutral wires separate throughout the electrical system except at the designated bonding point at the service entrance. If you encounter a situation where the ground and neutral wires are connected, disconnect them immediately and correct the wiring to comply with electrical codes. Here are some additional tips for preventing floating neutral conditions. Firstly, use proper wiring techniques. When installing or modifying electrical wiring, use proper wiring techniques to ensure that all connections are tight and secure. Use appropriate wiring connectors and tools to make reliable connections. Secondly, inspect wiring regularly. Periodically inspect electrical wiring for signs of damage, corrosion, or looseness. Pay close attention to connections in junction boxes, outlets, switches, and light fixtures. Thirdly, protect wiring from damage. Protect electrical wiring from physical damage by routing it through conduit or other protective enclosures. Avoid running wiring in areas where it could be exposed to moisture, chemicals, or extreme temperatures. Fourthly, use surge protection. Use surge protection devices to protect electrical equipment from voltage surges which can damage wiring and create floating neutral conditions. Fifthly, hire a qualified electrician. If you are not comfortable working with electricity, hire a qualified electrician to perform electrical work. A qualified electrician has the knowledge, skills, and experience to install and maintain electrical systems safely and effectively. When dealing with electrical issues, safety is always the top priority. Electrical work can be dangerous, and it's important to take proper safety precautions to prevent electrical shock and other hazards. Firstly, disconnect the power. Always disconnect the power to the circuit before performing any electrical work. Use a circuit tester to verify that the power is off. Secondly, use insulated tools. Use insulated tools to work on electrical wiring. Insulated tools are designed to protect you from electrical shock. Thirdly, wear safety glasses. Wear safety glasses to protect your eyes from flying debris. Fourthly, wear rubber gloves. Wear rubber gloves to insulate your hands from electrical shock. Fifthly, avoid working in wet conditions. Avoid working on electrical wiring in wet conditions. Water is a conductor of electricity, and working in wet conditions increases the risk of electrical shock. Sixthly, follow electrical codes. Follow all applicable electrical codes and regulations. Electrical codes are designed to ensure the safety of electrical installations. Seventhly, know your limits. If you are not comfortable working with electricity, hire a qualified electrician to perform the work. Finally, remember that electricity can be dangerous, and it's important to take proper safety precautions to protect yourself and others from electrical hazards. When troubleshooting electrical circuits, it is essential to have a good understanding of electrical theory and principles. This knowledge will help you accurately diagnose problems and safely repair them. Some key concepts to understand include voltage, current, resistance, Ohm's law, series circuits, parallel circuits, and grounding. Voltage is the electrical potential difference between 2 points in a circuit. It is measured in volts. Current is the flow of electrical charge through a circuit. It is measured in amps. Resistance is the opposition to the flow of current in a circuit. It is measured in ohms. Ohm's law states that the voltage across a resistor is equal to the current through the resistor multiplied by the resistance of the resistor. In a series circuit, components are connected end to end, so that the same current flows through each component. The total resistance of a series circuit is equal to the sum of the individual resistances. In a parallel circuit, components are connected side by side, so that the voltage across each component is the same. The reciprocal of the total resistance of a parallel circuit is equal to the sum of the reciprocals of the individual resistances. Grounding is the process of connecting electrical equipment to the earth. This provides a path for fault current to flow back to the electrical panel, tripping a circuit breaker or fuse and disconnecting the circuit in the event of a fault. A solid understanding of these electrical concepts will enable you to troubleshoot electrical circuits more effectively and safely. Also, familiarity with the National Electrical Code, known as NEC, is crucial for electrical work.